Forget the standard multi-line multiplication process involving shifting and summing intermediate products. The Trachtenberg system, devised under extreme duress, converts multiplication into a series of simple, localized additions based purely on digit position. This methodology eliminates the need to memorize multiplication tables beyond 5 times 5. The system relies on specific, streamlined algorithms for each multiplier, allowing the calculation to proceed sequentially from right to left. The final answer is generated one digit at a time, drastically reducing the working memory required compared to conventional methods. This efficiency stems from processing digits immediately and carrying the tens digit forward instantly, maintaining a single continuous calculation line. The rule for multiplying any number by 11 is simply neighbor plus self. To begin, we conceptually place a zero placeholder at both ends of the multiplicand. Starting from the rightmost digit, each resulting digit is the sum of the current digit and its immediate right-hand neighbor. If the sum is 10 or greater, the tens digit is carried over to the next calculation step. Consider 345 multiplied by 11. The rightmost digit 5 plus 0 is 5. 4 plus 5 is 9. 3 plus 4 is 7. 0 plus 3 is 3. The result is 3,795. This technique bypasses the need to write two lines and perform a final addition. Multiplication by 12 utilizes the rule double the digit plus neighbor. As before, zero placeholders frame the number. We start from the right. For each digit, we double its value and then add the digit immediately to its right. Any carry from the previous step is included before the addition of the neighbor. For 413 multiplied by 12, 3 doubled is 6. 1 doubled is 2, plus the neighbor 3 equals 5. 4 doubled is 8, plus the neighbor 1 equals 9. 0 doubled is 0, plus the neighbor 4 equals 4. The result is 4,956. This maintains the single-line right-to-left calculation structure, minimizing intermediate steps.
The rule for multiplying by 9 is subtract the digit from 9 and add the neighbor. The rightmost digit is treated differently, being subtracted from 10 instead of 9. Crucially, before applying the rule to any digit, the digit immediately to its left must be reduced by 1. Let us multiply 54 by 9. The rightmost digit, 4, is subtracted from 10, yielding 6. Moving to the 5, we first reduce the 0 placeholder to -1, which is handled by the carry. The 5 is subtracted from 9, yielding 4. We add the neighbor 4, resulting in 8. The final digit is the 0 placeholder reduced by 1, which is 4. The result is 486. This method is highly efficient because the subtraction from 9 is instantaneous. Multiplication by 8 is a variation of the 9 rule, incorporating doubling. The rule is subtract the digit from 9, double the result, and add the neighbor. The rightmost digit is subtracted from 10, then doubled. An additional rule applies. If the neighbor is odd, we must add 5 to the result of the doubling and subtraction. This parity check slightly increases complexity compared to the rule for 9. For example, multiplying 321 by 8. The 1 is subtracted from 10, yielding 9. Doubled is 18. We write 8 and carry 1. The 2 is subtracted from 9, yielding 7. Doubled is 14. Add the neighbor 1 plus the carry 1, totaling 16. We write 6 and carry 1. This systematic approach ensures rapid calculation without relying on traditional multiplication tables.
The rule for 7 is similar to 8. Subtract the digit from 9, double the result, and add the neighbor. If the digit is odd, add 5 to the result. The rightmost digit is subtracted from 10. The key difference from the 8 rule lies in the specific handling of the carry and the parity check application across the sequence. For instance, multiplying 234 by 7. 4 is subtracted from 10, yielding 6. Doubled is 12. We write 2, carry 1. 3 is subtracted from 9, yielding 6. Doubled is 12. Add the neighbor 4 plus the carry 1, totaling 17. We write 7, carry 1. This consistent application of localized rules across different multipliers is the hallmark of the Trachtenberg system. For multiplying two large numbers, the system employs a cross-multiplication technique, often termed the two-finger method. This method avoids generating multiple rows of partial products. Instead, it involves pairing digits from the multiplicand and multiplier, calculating their cross products, and summing them up, moving across the numbers from right to left. For instance, multiplying a 3-digit number by a 2-digit number requires calculating the sum of up to 2 cross products for each resulting digit position. The tens digit of the sum is immediately carried to the next position calculation. This technique maintains the single-line calculation philosophy, minimizing the memory required to hold intermediate results. The Trachtenberg system provides specialized rules for squaring numbers, often leveraging algebraic identities applied digit by digit. For squaring numbers ending in 5, the rule is straightforward. Multiply the tens digit by itself plus 1 and append 25. For general squaring, the system uses a method based on the expansion of a binomial squared, but applied sequentially. We calculate the square of the current digit plus twice the product of the digit and its neighbor. This process is executed from right to left, incorporating carries immediately. This direct squaring method is significantly faster than performing the full multiplication of the number by itself.
Trachtenberg division, known as the key number method, converts division into a series of rapid subtractions and additions, completely bypassing traditional long division. This method requires finding a key number based on the divisor. If the divisor is 88, the key number is 12, derived from 100 minus 88. The process involves multiplying the quotient digits by the key number and subtracting the result from the dividend. This effectively performs division by using multiplication and subtraction, which are the system's core strengths. The key number method is particularly effective for divisors close to powers of 10, such as 97 or 89. The speed of the Trachtenberg system is fundamentally rooted in its low cognitive load. It replaces multi-step operations, such as multiplication, shifting, and final addition, with single localized rules involving only addition, subtraction from 9 or 10, and doubling. This systematic approach minimizes the demands on working memory. By processing digits sequentially and carrying immediately, the system avoids the need to store large intermediate products. This makes it a highly efficient algorithm, specifically optimized for human mental computation, allowing complex calculations to be performed rapidly and accurately without reliance on extensive rote memorization.